I have a dream that one day
Hi there everyone, welcome to the first lesson on geometric progressions. In this introduction, we want to look at firstly the definition of a GP, secondly the fundamental property of GPs, thirdly the value of the nth term, then also the exponential nature of GPs, and lastly the sum formula. A geometric progression, also known as a GP or geometric sequence, is a sequence of numbers such that the ratio between consecutive terms is constant. Let's take an example. Let's take the sequence of numbers 1, 3, 9, etc. We multiply by 3 each time to get to the next term in the sequence, so the common ratio is equal to 3. Let's take a second example. Let's take the sequence of numbers 8, 4, 2, etc. We divide by 2 each time to get to the next term in a sequence. Another way of seeing this is we are multiplying by a half. So the common ratio in this case is a half. Let's have a look at what we mean by the fundamental property of GPs. If tk minus 1, tk, and tk plus 1 are 3 consecutive terms of a GP, then tk plus 1 divided by tk is the same as tk divided by tk minus 1. Let's again take the example of the sequence 1, 3, 9, etc. So we have term 1 which is 1, term 2 which is 3, and term 3 which is 9. Term 3 divided by term 2 is 9 divided by 3, which is 3. And term 2 divided by term 1 is 3 divided by 1, which is also 3. So from this we can see that term 3 divided by term 2 is the same as term 2 divided by term 1. We now want to come up with a formula for the value of the nth term of a GP. Let's consider the sequence with first term A and common ratio R. To get to the second term, we multiply the first term by R to get AR. Then to get to the third term, we multiply the second term by R to get AR squared. So the first term A is T1, T2 is the second term, which is AR, and T3 is the third term, which is AR squared. Let's look at these 3 terms more closely. T1 equals A, which is the same as AR to the 0, and this is the same as AR to the 1 minus 1. T2 is AR, which is the same as AR to the 2 minus 1. And T3 is AR squared, which is the same as AR to the 3 minus 1. Continuing with this pattern, we see that Tn, the nth term, equals AR to the n minus 1. So in the formula T sub n equals AR to the n minus 1, A is the first term, R is the common ratio, n is the number of terms, and T sub n is the value of the nth term. Let's look at the exponential nature of GPs, and let's consider the sequence 1, 2, 4, etc. So T1 is 1, T2 the second term is 2, and T3 the third term is 4. We can put this in a table, so when n is 1, T sub n is 1, when n is 2, T sub n is 2, and when n is 3, T sub n is 4. Plotting this on a graph, we see that we get a curve and not a straight line. Also note that we don't connect the points because n is a number of terms and it must be a natural number. Let's look more closely at the formula T sub n equals AR to the n minus 1. This is in the form y equals a times b to the x, which is an exponential equation where T sub n is y, r is b, and n minus 1 is x. Let's consider the geometric sequence AR squared, all the way up to AR to the n minus 1. The sum to n terms S sub n will equal A plus AR squared plus all the way up to AR to the n minus 1. This is also known as a geometric series. We can find the value of S sub n by using the equation S sub n equals A into r to the n minus 1 all over r minus 1, where r cannot equal 1, and S sub n is a sum to n terms. So let's look at the proof of the sum formula for geometric series. We are required to prove that S sub n equals A into r to the n minus 1 all over r minus 1, where r cannot equal 1. We start by writing out the sum to n terms. So we have S sub n equals A, the first term, plus AR, the second term, plus AR squared, the third term, plus all the way up to AR to the n minus 1. We call this equation 1. The next step is to multiply equation 1 through by r. So we end up with r times S sub n equals AR plus AR squared plus AR cubed plus all the way up to AR to the n. And this we can call equation 2. Now we subtract equation 1 from equation 2. So on the left hand side we have r times S sub n minus S sub n. Notice that on the right hand side, when we subtract, most of the terms will cancel, and we end up only with AR to the n minus A. Now we take out S sub n as a common factor on the left hand side and A as a common factor on the right hand side. Then the last step is to divide the r minus 1 on the left hand side into the right hand side. We also add that r cannot equal 1 because then we would be dividing by 0, which is undefined. 95% of problems that you'll encounter for GPs each fall into one of 9 categories. In the next few lessons, we will look at these in great detail. These categories are using the formula T sub n equals AR to the n minus 1, then using the fundamental property, using the sum formula, simultaneous equations, sigma notation, word sums, applications, mixed APs and GPs, and lastly, the sum to infinity. Example 1a says, find the value of the term as indicated for each of the following sequences. And in the first one, we have the sequence 1, 3, 9, etc. And we must find the value of the 10th term. So let's do that. We can start by checking to see whether it's a GP. So using the fundamental property of GPs, term 3 divided by term 2 is 9 divided by 3, which is 3. Then term 2 divided by term 1 is 3 divided by 1, which is also 3. So we know that it's a GP with common ratio 3. So the common ratio R is equal to 3. We must find the value of the 10th term. So we're going to use the formula for the nth term. T sub n equals AR to the n minus 1. And we want T sub 10. A is the first term, which is 1. R is the common ratio, which is 3. And n minus 1 is 10 minus 1, which is 9. So 3 to the power of 9. And it comes to 19,683. Let's look at the second sequence. We have 64, 32, 16, etc. And we must find the value of the 12th term. So once again, we can check to see whether it's a GP. So term 3 divided by term 2 equals 16 divided by 32, which is a half. And term 2 divided by term 1 is 32 divided by 64, which is also a half. So once again, we can see that this is a GP with common ratio R, in this case, equal to a half. And we must find the value of the 12th term. So using the formula for the nth term, so T sub n equals AR to the n minus 1. We want T sub 12. Now, A is the first term and is equal to 64. R is the common ratio, which is a half. N minus 1 is 12 minus 1, which is 11. And we can work this out on a calculator. And it's 0,03125. Let's look at your answer to the first question here. We have the sequence 2, 4, 8, etc. And we must find the 11th term. We're going to start by checking to see whether it's a GP. So term 3 divided by term 2 is 8 divided by 4, which is 2. And term 2 divided by term 1 is 4 divided by 2, which is also 2. So we know it's a GP with common ratio R equal to 2. We must find the value of the 11th term. So using the formula for the nth term, T sub n equals AR to the n minus 1. We want T sub 11. So it's A, and of course A is the first term, and that's equal to 2. So 2 times R, which is also 2, to the n minus 1, which is 11 minus 1, which of course is 10. And now we can find this on a calculator. And the answer is 2048. So 2048. In the second question here, we have the sequence 81, 27, 9, etc. And we must find the value of the seventh term. So once again, we can start by checking to see whether it's a GP. So term 3 divided by term 2 is 9 divided by 27, which is a third. And term 2 divided by term 1 is 27 over 81, which is also a third. So from this we can see that it is a GP with common ratio R equal to a third. We must find the value of the seventh term. So using the formula T sub n equals AR to the n minus 1. We want T sub 7. A is the first term, and that's equal to 81. So 81 times R, which is a third, to the n minus 1, which is 7 minus 1, in other words 6. And this we can find on a calculator. And the answer is 0,11, rounded off to 2 decimal places. So 0,11. Example 1b deals with finding the number of terms. So in the first question here, we are given this GP, so we are told that this is a geometric progression, and we need to work out which term equals 1 over 384. So let's look at this question. We can start by writing down what we have and what we need to find. We have the first term A, it's a third. We are told that this is a GP, so we can work out the common ratio R by, let's say, taking term 2 divided by term 1. So we have a fraction divided by a fraction. So we multiply the numerator by the inverse of the denominator. 3 into 6 twice, so this is a half. So the common ratio is a half. We need to find the number of terms, and we are told that the nth term, T sub n, is 1 over 384. So we can use the formula T sub n. So T sub n equals AR to the n minus 1. We know A is a third. So a third into R, and we saw that R was a half. So a half to the n minus 1 must equal T sub n, which is 1 over 384. We want to solve for n. So we can first get rid of the third here by multiplying both sides by 3. So we have a half to the n minus 1 equals 1 over 384 times 3 is 3 over 384. We can simplify the right-hand side. We can check whether 3 goes into 384. And it does. It goes into 384 128 times. So the right-hand side we can write as 1 over 128. So we end up with a half to the n minus 1 being equal to 1 over 128. This is an exponential equation with a power or index unknown. So we can try and make the bases the same. And by inspection, we can check that 128 is 2 to the power of 7. So this is 1 over 2 all to the power of 7. So we have a half to the n minus 1 being equal to a half to the 7. And now we merely use this exponential rule that says if a to the m equals a to the n, in other words, if we have an exponential equation and the bases are the same, then the powers must be the same. So then m must equal n. And using this rule here, the bases are the same on both sides, so the powers must be the same. So n minus 1 must equal 7, and hence n will equal 8. Now, just to go back to the question, it said, which term equals 1 over 384? We saw that n is equal to 8, so that means that the 8th term, t sub 8, equals 1 over 384. Before we go into the second part of this example, we want to have a brief discussion about logs. Now, let's say we need to solve this equation. A half to the x equals 1 over 128. We know that we can write 128 as 2 to the 7. So the right-hand side we can write as a half to the 7. So we have a half to the x equals a half to the 7. And as you may have noticed, we've made the bases the same on both sides. So if the bases are the same, the powers must be equal. We can drop the bases and x would be 7. What if instead we had a half to the x, so a half to the x, not equal to 1 over 128, but 1 over 130 instead. There's no way we can make the bases the same here, because 2 to no power will give us 130. In this case, we use logs. And what we do is we take the log on both sides of the equation. So the log of a half to the x equals the log of 1 over 130. And now we use a log rule. So this is the log rule. The log of a to the power m equals m times the log of a. So applying this rule to the left-hand side here, the x can go to the front and be written in front of the log. So we have x times the log of a half equals the log of 1 over 130. And now we divide the log of a half into the right-hand side, and we can solve for x. So x will equal the log of 1 over 130 divided by the log of a half. And this we can do on a calculator. So the log of 1 over 130 divided by the log, should be the log of a half. And this comes to 7,02, corrected 2 decimal places. So 7,02. So logs are useful to solve exponential equations with, where it's not possible to make the bases the same on both sides, and where we have to find the index or power as an unknown. Then also important to note about logs is let's say we have the log of a number x. Then if x is between 0 and 1, in this case a half is between 0 and 1, 1 over 130 is between 0 and 1. So if x is between 0 and 1, then the log of x will in fact be negative. This will become important for the second part of the example that we're busy with, especially where we are dealing with inequalities and we are dividing through by a log. So coming to the second part of this example then, we have this GP, the terms 8, 4, 2, etc. And we must find the number of terms that are greater than 1 over 1,000. Now, you should note that the terms are getting smaller and smaller, going from 8 to 4 to 2, etc. So at some point, we're going to get to a term in the sequence that will actually be less than 1 over 1,000. We must find out how many terms are more than 1 over 1,000. So let's have a look at it. We can start by writing down what we have and what we need to find. We have the first term a, that's equal to 8. We can get the common ratio r by taking term 2 divided by term 1, and we see r is a half. T sub n must be greater than 1 over 1,000, and we must find the value of n, the number of terms greater than 1 over 1,000. So we're going to use the formula T sub n. Now a is 8, so we have 8 times r, which is a half. We need to find n. This is the value of t sub n, and this must be greater than 1,000. We can simplify by first getting rid of the 8 here. We can divide the 8 into the right-hand side. And on the right-hand side, we'll get 1 over 8,000. So what we're saying is we have 1,000 divided by 8, which is the same as multiplying by 1 over 8. And that gives us 1 over 8,000. Now, there's no way we can make the bases the same in this inequality. So we're going to use logs. We're going to take the log on both sides. And now we're going to use this log rule. The log of a to the m equals m log a. And we can write the n minus 1 here in front of the log by using this rule. So we'll have n minus 1 times the log of a half is greater than the log of 1 over 8,000. We want to solve for n, so we can divide the log of a half into the right-hand side. Now, here, the argument, in other words, if we have the log of x, then x is called the argument. Here, the argument is between 0 and 1. So the log of a half will be negative. And since we have an inequality and we're dividing through by a negative number, the inequality switches around. And we can work this out in a calculator. So we have the log of 1 over 8,000 divided by the log of a half. And this comes to 12,97, rounded off to 2 decimal places. So then n minus 1 is less than 12,97. And we can take the negative 1 to the right-hand side. So n will be less than 13,97. N, of course, is a number of terms, and it must be a natural number. So the natural number closest to 13,97, but smaller than it, will be 13. So n will equal 13. So that means that there are 13 terms that are greater than 1 over 1,000. So the 14th term in this sequence will actually be more than 1 over 1,000. So let's look at your answers to this question. In the first one it says, given the following sequence, 30, 10, 10 over 3, etc., determine n if the nth term is 10 over 729. We can start by writing down what we have and what we need to find. We have the first term a, which is 30. We can get the common ratio r by taking term 2 divided by term 1. And that's a third. We are given t sub n, the value of the nth term. It's 10 over 729. And we must find the value of n. We're going to use the formula t sub n equals ar to the n minus 1. And a is of course 30. R is a third. We don't know n. And t sub n is 10 over 729. We need to solve for n in this equation. We can first get rid of the 30 on the left-hand side by dividing it into the right-hand side. Now, 10 over 729 divided by 30 is the same as 10 over 729 times 1 over 30. Of course, we can cancel 10 into 30. It goes thrice. And we're left with 1 over 729 times 3 on a calculator is 2187. So we end up with a third to the n minus 1 equals 1 over 2187. We have a choice as to how we want to proceed from here. We can try to make the bases the same on both sides by using inspection to see 3 to which power gives us 2187. Or we can use logs. Now, we're generally always going to use logs because that's simpler or easier. We can take the log on both sides of the equation. We now use the log rule that says n minus 1. This power can be written in front of the log. So n minus 1 times the log of a third equals the right-hand side. Now we can divide the log of a third into the right-hand side. So n minus 1 equals and this we can do on a calculator. So we want the log of 1 divided by 2187, all divided by the log of 1 divided by 3. And our answer comes to 7. And hence n will equal 7 plus 1 or 8. So n equals 8. Let's look at your answer to the second question here. We are given this GP, 3, 2, K, etc. And in the first question, we have to write down the common ratio, or the value of the common ratio. Now, that's quite easy because R, the common ratio, we can get by taking term 2 divided by term 1. So it's 2 over 3. In the second question, we must find the value of K, the third term. So K equals the third term, and we can get the third term by taking the second term, in other words 2, and multiplying it by the common ratio R. So 2 times 2/3, which is 4 over 3. Then in 2.3, we have to find the value of n if t sub n is 128 over 729. So let's start by writing down what we have and what we need to find. A is the first term, and we know that that's equal to 3. R is the common ratio, and we worked out that it's equal to 2/3. The value of the nth term is given. That's equal to 128 over 729. And we must find the value of n. So we're going to use the formula for the nth term. And we can substitute in our values. A is 3. R, of course, is 2/3. N is what we need to find. And t sub n is 128 over 729. We need to solve for n in this equation. We can first get rid of the 3 here by dividing it into the right-hand side. Now 3 doesn't go into 128. So we're going to take 128 over 729 and multiply it by a third. So 128 times 1 is 128. And let's see what 3 times 729 is. It's 2187. And we're going to take the log on both sides again. And we can use the log rule that says the n minus 1 can be written in front of the log. Then dividing the log of 2/3 into the right-hand side. all divided by the log of 2/3. And on a calculator, the right-hand side comes to 7, and hence n equals 7 plus 1, which is 8. Let's look at your first answer here. We have the GP 2, 5, etc. And we must work out which term is equal to 6250 over 32. So let's start by writing down what we have and what we need to find. The first term A is 2. The common ratio R we can get by taking term 2 divided by term 1. So 5 over 2. We're given the value of the nth term. It's 6250 divided by 32, or over 32, and we must find n. So using the formula T sub n again, we can plug in A is 2, R is 5 over 2, and it's to the n minus 1, and that's equal to T sub n, which is 6250 over 32. We can divide by the 2 on the right hand side. So that's 6250 over 32. Dividing by 2 is the same as multiplying by a half. Now we can take the log on both sides. So the log of 5 over 2 to the n minus 1 equals the log of the right-hand side. We can use a log rule and write n minus 1 in front of the log on the left-hand side. And we can write the log of 5 over 2. We can divide by this on the right-hand side. So n minus 1 is the right-hand side divided by the log of 5 over 2. And this we can work out on a calculator. And it comes to 5. So n minus 1 is 5, and hence n is 5 plus 1, which is 6. Now, to go back to the question, they wanted to know which term of this GP equals 6250 over 32. So this is in fact the 6th term. In the second question here it says, calculate the number of terms in the geometric series, and we are given the series. So once again we can start by writing down what we have and what we need to find. The first term A is 0,03. We can get R by taking term 2 divided by term 1. And this is equal to 2. Then the last term, or the nth term, T sub n, is 1,92. And we need to find a number of terms. So the value of n. Using the formula T sub n again, we can plug in the values. A is 0,03, R is 2, and T sub n is 1,92. So we can get rid of the 0,03 by dividing it into the right-hand side. Let's see what that comes to. And it comes to 64. So 2 to the n minus 1 is 64. Now, in this case, we can use logs again, but it's probably easier just to write the right-hand side with base 2, because we know that 64 is 2 to the power 6. So we have an exponential equation where the bases are the same, so the powers must be the same. Hence, n minus 1 is 6, and n is 7. So there are 7 terms in the sequence. In number 3, we are given this GP, and we have to find the number of terms that are greater than 1 over 250. So let's have a look at it. The first term A is 81. We can get the common ratio R by taking term 2 divided by term 1. And R comes to a third. We want T sub n to be greater than 1 over 250. And we must find the value of n. So we can use the formula T sub n equals AR to the n minus 1. We can plug in our values. So A is 81, R is a third. We have to find n, and this is T sub n, so it must be greater than 1 over 250. We need to solve for n in this inequality, so we can divide the 81 into the right-hand side. So let's see what that comes to. So it's 1 over 20,250. Of course, what we're doing here is we're taking 1 over 250 divided by 81 will be the same as 1 multiplying by 1 over 81. We can now take the log on both sides. And the n minus 1 can be written in front of the log by the log rule. We want to isolate n on the left-hand side, so we can divide the log of a third into the right-hand side. But what's important to note here is that a third is less than 1. It's between 0 and 1. So the log of a third will be negative. And when we divide through an inequality by a negative number, it switches around. So divided by the log of a third. And this we can do on a calculator. and it's 9,03 rounded off to 2 decimal places. So 9,03. And solving for n will be less than 10,03. N, of course, is the number of terms. It must be a natural number. So the number closest to 10,03, but less than it, that is natural, is of course 10. So n will equal 10. So then to go back to the question, we needed to find the number of terms greater than 1 over 250. So there are n, or rather 10 terms that are greater than 1 over 250.